Hey guys, welcome to Intersections 1, Unit 3, Section 3. In this lesson, we're going to learn to determine the intersections of lines and planes in R3. We're also going to look at lines and planes eventually. But for now, for this lesson, we're going to work with just lines and planes. So, there are three possibilities that can occur when you have a line and a plane. Really, the line can go clear through the plane and intersect it at point P, right here. Or the line can be parallel to the plane, okay, but not inside the plane, like it is in this case, right? So for case 3, here we have a line that's literally inside the plane, or the plane contains the line L, right? Whereas here, the red line L, right, is running along the top, right, running us above the plane and is parallel to the plane, so it would never intersect. And it has this unique property of, in this case, being perpendicular to the normal of the plane, okay, which you can see here. So these are the three possibilities, and what we're going to do next is learn how to determine which is which when we're given, literally, their equations. Okay, so when we're given the parametric equations of a line, like this, and a plane, and we're asked to find the intersection, if any, this is probably the most simple situation that can arise, because we have, in this case, we've been given parametric equations, an expression for x, y, and z, three expressions here that represent all points on the line. And with this Cartesian equation of a plane, we have an x and a y and a z in it already. And so the process of finding an intersection is literally just to substitute each of the parametric equations for x, y, and z straight into the plane. So let's go ahead and do that. So we get 3 times x, which is 4 minus t, minus y, which is 5 minus t, and finally plus 2z, which is 3 plus 2t, plus 3 equals 0. And you'll see now that what we have is an equation in terms of t, right? And so at this point, we need to solve this equation and figure out if there's a consistent value for t, if there's a parameter that we can use to determine the point on this line that coincides with the plane. So let's go ahead and do that. So of course we're going to get 3 times 4, which is 12, minus 3t. Go ahead and expand this all out. Minus 5 plus t plus 6 plus 4t and plus 3 equals 0. Okay, so next we can collect like terms. So once we do this, we end up with 16 for our constant and 2t for the value, for the linear term, and this is equal to 0. And so 2t equals minus 16, and t equals negative 8. Okay, and so this is the parameter that we would have to use, right, in our parametric equation here. That means if we set t to 8, negative 8, then we should get the point that we want that's on our plane. So, so we can say, therefore, okay, the point of intersection is, well, it's going to be x equals 4 minus negative 8, y is equal to 5 minus negative 8, and z is equal to 3 plus 2 times negative 8. Right, and so here we get 12, 13, and negative 13. And so the point of intersection is 12, comma 13, comma negative 13. Okay, let's look at example 2. So we're going to use the same method here. So let's start with, first of all, by writing parametric equations. And we'll put this nice and far over to the left here because we need lots of space for these. So x is equal to, well, in this case, it's just going to be 4, right? Because we have 0 times t. And let's write y. So y is equal to 3 plus 2t, and z is equal to negative 1 plus t. Okay, zoom in a little bit. There we go. So now what we can do is input these three things into the plane. And so we're gonna have 3 times 4, right, minus 3 plus 2t plus 2 times negative 1 plus t plus 3 equals 0. Okay, and so we'll have 12 minus 3 minus 2t minus 2 plus 2t plus 3 equals 0. And so the thing to notice here, right, is that we've got a minus 2t and a plus 2t. Right? So when this simplifies, we're going to be left with, well, the t terms are going to be gone, and we're going to have these constants left over. And when we add them together, well, we're going to have, let's see, we're going to have minus 3 plus 3. Those are going to be gone. 12 minus 2 is 10. Right? So we're going to have 10 equals 0, which is false, never true. And if you get a false statement, okay, once you plug this in, what that means is there's no value of t that could ever satisfy this plane, okay, x, y, and z. And we have this situation here, case 2, where this line is parallel to, but not on the plane, okay? So we can go ahead and say, therefore, right, no intersection. And we could even be more specific. We can say the line is parallel, but not, or sorry, parallel to, or just parallel and distinct would do it. Yeah, parallel and distinct, which means different. Okay, let's look at example 3. So following the same process here, well, we're going to end up with the same, or actually no, different parametric equations because we have a different point here, right? Same direction vector. So of course x is going to be just this value here, which is 1. Y is equal to 8 plus 2t, and z is equal to 1 plus t. Now when we put these in, we get something else. We're going to get 3 times 1 minus 8 plus 2t plus 2 times 1 plus t plus 3 equals 0. Okay, and so we get 3 minus 8 minus 2t plus 2 plus 2t plus 3 equals 0. And notice how our t's are still going to cancel, right? Minus 2 plus 2t. But this time, all the coefficients should cancel, right? 3 minus 8 is negative 5, plus 2 is minus 3, plus 3 is 0. And so all of this on the left adds to 0, and we get 0 equals 0, which is always true, right? And I wrote that in capital before. We'll write it in capital this time. Here we go, capital letters. Right, so because we got a true statement, something that's always true, regardless of t, what that means is that every single value of t will satisfy this equation because t doesn't matter. Okay, in other words, we could put any t in here and it doesn't matter because this negative 2t is going to cancel with that plus 2t, right? And this is the third case where the line is literally inside the plane. And when the line is inside the plane, we could literally take any t on this line, right? Any multiple of the direction vector for this line, and we would reach a point that's on the plane as well. So every point that's on the line also intersects with the plane, right? And so we can say true, therefore, the intersection is the line. And the line, or the plane, contains the line. And that's nice and specific. Okay, so let's look at the intersection of lines now. Okay, so when you have two lines in 3 space, really there are 4 options. You can have a point intersection where they connect at some random point A. You can have the case where they're both the same line, coincident lines. Remember, right? Lines in 3 space can have different vector equations, but refer to the same line. You can have parallel lines where their direction vectors are collinear, but the lines do not touch, and therefore there is no intersection. And of course you can have another case where they are skew. Now skew lines means that they are not parallel and they do not connect at any points. They kind of miss each other, skew lines. And of course for case 2, I should have said that the intersection is all the points on the line. Now before we get to these, what I want to do is look quickly at finding intersections in 2 space. So in grade 9 when you did this, when you're given 2 lines and told to find an intersection, it was really just a matter of solving them for y, right, and equating them and then solving them for x, right? So in other words, if we had something like y equals x plus 1 and y equals 2x minus 1, right, you could equate these, equate the y's, so x plus 1 equals 2x minus 1, solve for x, and you'd get your x coordinate of the point of intersection. So really, equating them is the way to go, and really it's the same strategy for both 2 and 3 space when you're working with vector equations. And you can, you could use this whole process here in 2 space, write these in Cartesian form, right, and then equate them, but you can also just equate the vector equations. Watch, right? So what we can do is we can say let line 1 equal line 2. And then we can take our vector equation 4, 2 plus m times negative 1, 3 and equate that with 5, negative 1 plus n, n times 2, negative 6. There we go. And we can solve this because really we have a bunch of components here whose values we can add up. We can actually create 2 equations, right? Because we know that on the left side here we're going to have this is really just going to be 4 minus m, 2 plus 3m is going to be equal to 5 plus 2n. And negative 1 minus 6n. Okay, and from this, we know that we have 2 equations. Really, this must equal that, and this second y value must equal this y value. So 4 minus m should equal 5 plus 2n. And 2 plus 3m should equal negative 1 minus 6n. So this is really just a little system of equations, right? We can number each of these, and we can solve them using substitution or elimination. So why don't we triple number 3? We'll go 3 times 1, and we'll add that to 2, and see what happens. Okay, so we're going to have, 3 times 4, which is 12, plus 2, which is 14. Then we're going to have minus 3 times m plus 3m. So that's going to cancel, right? So that's equal to, again, 15, right, minus 1, which is 14. And then 3 times this is 6 minus 6. So that's going to be 0. So look at that. We ended up with just 14 equals 14, which, again, is true all the time, right? And if this is the case, we know that we actually must have had the same line, right? L1 is equal to L2. And so we can say, therefore, okay, the lines are coincident. Okay, let's just draw a line here. Now you might ask, well, do I have to state that the intersection is the line? Well, I think that probably if you've got this far and you tell me that they're coincident, I'll assume that you know that means that they are in fact the intersection is the whole line, right? Because they're the same line. All right, let's look at L1 and L2. So here, what I'm going to do is kind of skip some of these steps here. We'll first of all say let L1 equal L2. But next, what we'll do is just set up our parametric equations and equate the lines in the same step. So we know that 0 plus q, right? 0 plus q, that's our x value for line 1. That's going to have to equal the x value from line 2, right? So that's going to be minus 2 plus n. And then we're going to have y values that we want to equate, right? So negative 3 minus q is equal to 1 plus n. All right, let's call this 1 and call that 2. And again, here we can use substitution or elimination. In fact, it's easy here just to add these, right? You see we have a plus q and a minus q, right? So let's do that. So we're going to end up doing 1 plus 2, which yields, well, 0 plus minus 3 is negative 3. Those guys cancel out, the q's, and then we're going to have minus 1 and 2n. Okay, so let's solve this. Well, if we bring that negative 1 over, we're going to get positive 1. So we're going to get negative 2 equals 2n, and therefore n equals negative 1. Very good. All right, and so what this says is hey, there's a point on, well, we got an n value, right? It just happened to work out that way because we eliminated q. We could have eliminated n by subtracting these and gotten a value for q as well. But in any case, if there's a point of intersection on one line, it's also going to be on the other line anyway. So really, this value of n is what we can use in line 2 to produce the point that we want, right? So let's do that. So we can say therefore, right, x comma y is equal to, and I'll just go down the line here, it's going to be equal to negative 2 comma 1 plus negative 1 times 1 comma 1. Right, so this will be equal to, let's see, negative 2 comma 1 plus negative 1 comma negative 1, or minus negative 1 comma negative 1, but, or positive 1 comma 1. Really, we can add these up. We're going to have negative 3 comma 0. And so we can say, therefore, the point of intersection, POI, is negative 3 comma 0. Now, in 3-space, we're going to follow the same process by equating the lines using, by equating all their components, and then solving the system of equations that results to see if there is a parameter that on one of the lines that we can use to get a point. So let's go ahead and do that. Oops, there we go. So page 3, investigation 3 says determine the intersection, if any, of the following pairs of lines in R3. So let's start with this one here in the top left. So we'll say let L1 equal L2. And this time, we're going to have to equate all of the parameters, right, in parametric form. So the x values are 1 plus p, right, 1 plus p, which should be equal to 3 plus 2q, right? So that was our x values. Then we're going to equate the y's, right? So we're going to have 2 plus 0p. So 2 is equal to, and here y will be 4 plus. Notice how we have a 0 here as well, right? So this is going to be 4. And right away, okay, for this one, we can see here that we got something that's false, right? As soon as you do this, right, if this breaks down at this point and you get something that's false, what this means is that you've already found that these two lines do not intersect. Now, really, this could mean, okay, either of these two cases, case 3 or case 4. And so it's a matter of determining which is which. So let's go look here for a moment at the equations. Well, we can look at the direction vectors to determine if they're parallel, right? Remember how, right, if one vector is a multiple of another, then we know that they are collinear. So is that the case? Well, here we have 2, 0, negative 4, which is really just double this one, right? So if we called this one D1, right, and we called this one D2, well, we could say since D2 is really just 2 times D1, therefore the lines are not skew, they are parallel and distinct. And of course this means that there is no intersection. Okay, let's look at the next one. Okay, so for the next one, we're gonna have the same thing going on. We're gonna say we'll let L1 equal L2. Let's see what we get. So we'll start with our x's. So 1 plus 2m is equal to, in this case, 2 plus n, right? 2 plus n. And then we're going to have 2, this is for our y's now, 2 plus 3m equals 3 plus 2n. And then we're going to get 3 plus 4m is equal to 4 plus 3n. Okay, let's call these 1, 2, and 3. Now what we have here is 3 equations in 2 variables. Now if we had 3 equations in 3 variables, right, then we would have a full-blown matrix, right? We would need to do some pretty advanced either Gauss-Jordan elimination or back substitution. But since this is really just this is really only 3 equations in 2 variables, it means that we're just going to have to solve 2 of them, right? And then check the third one to make sure that it's consistent. Let's simplify here a little bit, right? So this one, of course, we have some constants that we need to clean up. This one's going to become 2m is equal to 1 plus n, right? And then this one will become 3m is equal to 1 plus 2n, and 4m equals 1 plus 3n. Okay, so what's next? Well, why don't we work with equations 1 and 2? What we can do is we could eliminate n, right? Let's go 2 times 1 minus 2. Right? And that's going to give us the following. Well, 2 times 1, if we double this one and subtract this, we're going to get 2 minus 2, that's 0, right? And then here, 2 times that is 4 minus 3, that's only 1, so we're going to have m. And then here we're going to get a 1, of course, and then this is going to be 0, right? So really we just have m equals 1. Well, that's handy. Let's plug this in, right? Plug this into, well, we could use either equation here to find n. Let's use this one up here, right? So we're going to plug this into sub m equals 1 into 1, right? And so we'll use this rearranged version of 1. So we're going to get 2 times 1 equals 1 plus n, or really 2 equals 1 plus n, or n equals 1. Okay, so we got m equals 1, n equals 1. But really, we've only worked with equations 1 and 2. So we need to check and make sure that this is also, right, m and n are also, will satisfy equation 3. All right, so let's do that. So let's check, we'll check 3, right? So our left side will be equal to, and we can use this, right? It's 4 times m, which is 1. And our right side is equal to 1 plus 3 times 1. So this is really just going to be 4, and this is also going to be 4, right? And this is equal to left side, which is good. Okay, so now that we have an m and an n value that's consistent, what this means is we have a parameter for each line that should give us the same point when used. So let's check this, right? So L1 is going to be equal to, come on, where are we? There we are. Okay, L1 is going to be equal to, well, it's going to be 1, 2, 3 plus 1 times 2, 3, 4. And it should kind of already it should be obvious already at this point, I think, that 2, 3, 4 plus 1 times 1, 2, 3, 1, 2, 3. In either of these cases, we're kind of just adding the same coordinates, right? So this is going to be 3, 5, 7 in either case, right? 3, 5, 7. So, therefore, right, we can say, therefore, the points of intersection is 3, 5, 7. Okay, so we have one more example here. L1 and L2. This time we have 1, 2, 3, 3, 4, 5, and we have these direction vectors here that follow parameters g and h. Well, let's use the same method and see what we get this time. Okay, so let's equate these. So let's start with the x's. So the x for line 1, parametric equations for line 1 for x would be 1 plus g, right? And that would be equal to 3 minus h. We'll just call that equation 1 straight up. And the y value, so we're going to have 2 minus g equals 4 plus 2h. Equation 2. And then we're going to have, let's see, what's next? So we're going to have 3 plus 5g. Thanks to Huawei. My little joke there. So, and then we're going to get 5 minus 2h, which is equation 3. Okay, we could start this one by adding 1 and 2, right? Because we have we've got a g and a negative g there. So let's add those equations, and we're going to get 3 equals 7 plus h, or h equals negative 4, right? And we could use this, we could plug this into equation 1 to get our g value. So we'll take this, plug it into 1. So we're going to get 1 plus g equals 3 minus negative 4. And 1 plus g equals, well, that's going to be 7. And so g equals 6. All right, great. So we got an h and a g. And we got that out of equations 1 and 2, right? You have to be careful here that at this step, that you're not plugging that into equation 3. Why is that? Well, the reason is because we've eliminated, right? We've eliminated a variable using equations 1 and 2, and we don't really want to touch 3, right? Until we get to the end, until we have a g and an h that arise out of the two equations that we're working with initially. So, so stick to 2 equations until you have a value for each parameter, then check equation 3. So let's go ahead and do that now. So we'll check 3, and let's see. So our left side is going to be equal to 3 plus 5 times 6, right? And our right side is going to be equal to 5 minus 2 times negative 4. So this one would be 33, and this one would be, so that's going to be 8, right? It's 13, which is not equal to the left side. And so because this happened, right, because this h and g actually did not satisfy equation 3, what this means is that g and h are not consistent throughout the system. In other words, these parameters actually wouldn't yield us the same point if we use them in these lines. So that leaves us with the same question as the last one. We have to say, is this a case of parallel lines or skew lines? And of course, we found they were parallel last time, so maybe we have skew lines this time. So what do? Check the direction vectors, right? Here they are. So 1, negative 1, 5, negative 1, 2, negative 2. So can we write one as a multiple of another? Clearly no, right? We can't just take this one and multiply by negative 1 because while that would work for here, it's not going to work there, and it's not going to work there, right? And so what we can say is, since, right, D1 is not equal to a multiple of D2. These should be vectors. Therefore, the lines are skew, and there is no intersection. So that wraps up our lesson on intersections 1, lines and planes. There's practice questions here on page 496. Go ahead and use the remaining time to work on those, and we'll see you guys next class day.